What's up, everyone? It's Matt Martin with the Grass Factor. I want to do a little video today talking about CRRP technology. All right, so why I wanted to do this video is Paul did an awesome video about it, and Paul, we really appreciate that. We didn't expect that. We just kind of wanted you to see the before and after and the things we've been working on over winter. So, needless to say, cat's out of the bag. Okay. So anyway, today I wanted to talk about the CRRP technology, right? And exactly what is it? So this is kind of what our new thing is going into 2019. All of our products are going to be based on this CRRP technology. So I want to give a brief rundown. I think Paul did a great job of actually explaining what it is, but I want to explain why we chose each individual component in the product that we actually chose. And so to start this off, I think, really, first and foremost, what is it? What is CRRP technology? CRRP technology is carbon release root promoting. And part of that whole process is the homogenization and co-composting of biochar with poultry manure. And I think this whole thing kind of starts really with why co-compost biochar, right? So we knew we wanted to work with biochar because of the results I had, way back when, starting with athletic turf, but then why does this co-composting take place, right? Why do we do that? And we put a lot of time into researching this, but this is an example study here that you come across, and this was in the International Journal of Environmental Science and Technology, and basically it showed that using biochar, you could effectively absorb nitrate, phosphorus, and potassium. So that told us two things. One, nitrogen and phosphorus are going to be anions, meaning they have a negative charge, potassium being a cation, meaning positively charged. So this would give us the flexibility to capitalize on both the anion exchange capacity in the soil and the cation exchange capacity of the soil. And then this particular study here showed that when homogenized together with biochar, it actually did slowly release. It actually demonstrated slow release behavior. So this kind of, and actually we found out this study like here really recently. So anyway, I was super excited to find it, and it gave us credence to what we already interpreted that was actually taking place. So we know biochar has the ability to absorb and store nutrients, and for us that means longevity, right? So when we efficiency is going to be the word that I like to use for that. And when I say efficiency, meaning when you apply a pound of nitrogen, you get as close to a pound of nitrogen that gets delivered to the plant. And why does this happen with biochar? Part of it, in terms of slow release, is going to be due to that porous structure, those microstructures that occur as nitrogen or phosphorus or potassium move into those pores. One, water does not filter through it very, very well, and so the reduction of water moving through it means less of it can become soluble, because in order for the plant to be able to take it up, if it's not taking it in through the leaf, right? So how much is actually going to be taken in through the leaf? Well, depending on the nutrient, it may only be a 30%, it may only be 2%. So with solubility, the rest of it is taken up through the root system, right? So, but in order for it to be taken up through the root system, it has to become solubilized. So if you use a carrier to affect the solubility of nitrogen, ultimately you can affect the uptake of the nitrogen. So if we look at like a polymer coating is going to protect your urea or whatever nitrogen source it may be, or whatever nutrient source it may be. The polymer coating would inhibit the amount of water that it comes in contact with, therefore inhibiting the solubility, therefore inhibiting the plant's ability to take it up. Then the added capacity of the biochar is that also what doesn't get taken up through the root system, it actually has a home to fall back into. So instead of necessarily leaching out from the soil system, it already has something that's adsorbative there, that's sponge-like, to be able to take it back in and house it until next irrigation event or the next rain event. So it creates this capture and release like effect. So if it doesn't get utilized by the plant immediately, it's got somewhere to house and hang on to. to the next event. When it does become solubilized and it's not taken up by the plant, it has somewhere else to go. And then, of course, the added agronomic benefits of compost. Compost performance in turf is not really something that has been debated a whole lot. You're not going to really find a whole lot of information out there that shows compost is bad for turf unless you're using bad compost. So, a couple studies here at University of Illinois, it was great. Compost additions in general improve both soil properties such as soil tilth friability, ultimately improve soil drainage as well as increase germination rates. Penn State, another great turf school. In clay soils, good quality compost will improve structure, reduce surface crusting and compaction, promote drainage, and provide nutrients. In sandy stools, increases water and nutrient retention, so on and so forth. A couple more universities here. University of Florida. University of Florida says, again, you got sandy soil down in Florida. This would be a great one to add to it. Great soil amendment. Ohio State, they did a little more in-depth multi-year study on it. They found that clipping yields, color, and foliar nitrogen concentrations were all positively affected for up to 50 days after top dressing with locally available composted sewer sludge. So this particular one here, they actually use like a biosolid like compost. So why specifically poultry manure? To be quite frankly, one is availability. And if you kind of pay attention to what goes on in different parts of the United States, in certain areas where poultry manure is dominantly used, there is in agriculture, there's an oversupply of it there for agriculture, and very little of it makes it to the turf market. So the way we look at it is that it allows us to take a waste stream, what would be wasted, right? Because so much of it's going to have to be landfilled because the fields can only take so much of it because phosphorus levels become elevated and that can leach. So for us to be able to distribute it across lawns across America, what happens is that we distribute it from being piled up or landfilled to leach phosphorus to move it to other parts of the country that could be phosphorus deficient or would just benefit from having a composted material applied to turf. So that way it's moved from fields that it's constantly applied to areas of the country where it's not normally applied. This first study here is actually going to compare hay yield, the Bermuda grass yield on hay as relates to ammonium nitrate versus poultry litter with an equal end-to-end type ratio here. Then you can see you get pretty close to similar results. Year number one, quickly out of the gate, you got your biggest performance impact. So this is going to be your first cutting of the year. You get your biggest performance from your poultry litter. The second cutting, that's when you got your biggest performance from your ammonium nitrate. But at the higher rates, you can see you were still getting pretty good yield out of your poultry litter. And then cutting number three, pretty much across the board, no matter the rate, you can see a pretty sharp, drastic decline there. However, moving into year two, you can see, that second and third cutting are actually still pretty significant. And over a 2-year study, there's not really a whole lot of statistical difference between the two products. So at that point, it kind of paints the picture there that it does work as a substitute for fertilizer. But I think what's most important here is that it shows that you can actually blend the two and cut down on the amount of high salt content fertilizer that you have to apply. Not that there's anything wrong with ammonium nitrate or ammonium sulfate or any of that. It's just it is a salty fertilizer. So by being able to run a combination of the two, then you can balance your salt content with something that is going to promote your rhizosphere, your microbiology in the soil. Now, it kind of brings us back to that question, why do we co-compost them together? And when we were doing our research, this is actually after we had already formulated our product, we came across what University of Minnesota was doing, and University of Minnesota was researching biochar at the time specifically for the intent of becoming a fertilizer, how to incorporate it into a fertilizer program. And one of the things they looked at was how biochar could have a greater agronomic impact. And they got their greatest agronomic impact from biochar when it was co-composted. Specifically, in their test, they used manures. And they used a variety of manure. So part of it was like horse, poultry, and one other, I can't recall what it is. So by co-composting these two together, one, it actually sped up a bit of the composting process, converting the organic material in the manure into humus. And then from that humus state, it actually, that process of degrading from an organic matter, a raw manure, into a compost, it actually coated the biochar with an organic coating. And what's important is that it's that coating that improved the properties of the biochar that contribute to nutrient storage and the formation of soil organic matter. And more importantly, where we'll see later on, is that it actually contributes to the ability for not only the biochar to absorb nutrients, but also to release nutrients. Back to that kind of idea of biochar being used as a slow-release fertilizer, one of the first things they did here was they tested nitrate content in the biochar after the co-composting process. And so what they found was that during conventional extraction, they could only get about 43% of the nitrate out of the biochar. Something was impeding that extraction from taking place. It took over a period of 96 hours of that extraction in order to remove it, whereas the pristine biochar, it actually happened relatively instantly. So this, again, confirms the idea that biochar would function as a slow-release fertilizer. Kind of deeper reading into this, the enhanced interaction of co-composted biochar with water, the hydrophilicity of the organic coating decreases biochar's hydrophobicity. So it takes it from a point of repelling water and difficult for water infiltration, and in turn makes it a little easier for the water to pass through it, therefore making it easier to solubilize those nutrients that exist in the biochar. And I love this final ego-stroking final sentence right here. Co-composting a biochar with nutrient-rich feedstock or other ways of treating nutrient-rich waste streams with biochar, example, liquid manure, is therefore key to increasing biochar's agronomic value. Yes, please. And again, more ego stroke here with this whole thing, again, out of the University of Minnesota. They concluded that the combination of biochar with non-pyrogenic organic matter, example, manure, is the key strategy to develop carbon fertilizer carriers that are effective at low application rates. Annual application of such biochar-based fertilizers could sequester carbon and mitigate global warming, a global mitigation strategy that could be implemented due to its economic value for farmers without the necessity for further subsidies. And why this actually was important for me is because if anybody knows me, one of the great things that would just be unbelievable in this world to me are the number of people that have come after me and said turf grass is going to be the downfall of the environment. Turf grass management is such a luxury that it's single-handedly destroying the environment. Now, it's not tons and tons of people, but it's enough of them that it keeps me awake at night. And when I quote studies about how an acre of turf grass sequesters more carbon, 4x more carbon than an acre of forest, and I get so much hate for it, and I get kicked off Facebook for it, and we actually lost our company Facebook page for such statements, and I pulled that directly out of a study. I had to read something like this out of a university that's done years and years and years of research on biochar, and again, we're now developing a fertilizer that can be used in turf that the fertilizer alone could directly impact the carbon sequestration that takes place, along with the performance of turf grass, which again is a great carbon sequestration tool. Then all of a sudden, what if biochar? No. Let me take that back. What if turf grass could be a solution to an environmental issue we may be in? Interesting. Okay, so I'm going to clear myself off the picture here so you can see this. A little bit further into the study, and this is what I really liked about this, is they actually compared a nitrogen, phosphorus, and potassium program, an NPK program, as a base. That was the control, NPK. Then, in combination with it, they added varying types of biochar type products. So one, for instance, would be biochar composted with manure, biochar composted with manure and compost, fresh biochar, and a control of only the NPK. And again, the common denominator here is that this same NPK program was applied to all the plots. And so we have two varying degrees of fertilizer that were applied here, including a micronutrient solution that was applied at 54 days after seeding. Again, this was also done on quinoa. Just to make that clear, this was done on quinoa. We have a 4-4-3 analysis of N to P to K here. So 4 parts nitrogen to 4 parts potassium to 4 parts phosphorus to 3 parts potassium. And again, we got our micronutrient complex here. And those are EDTA chelated micronutrients at that too. So just to show that those were most likely used when applied foliarly. And let's take a look at the results that came from this. Okay, so first, this shows the leaf nitrogen percent available, right? So how much nitrogen is actually making it into the plant. And why this is important is because the one common denominator here is that NP and K were applied to all of these. So in order to, what it shows here is that the biochar that's been co-composted was able to allow more nitrogen to make it into the leaf. And why did that occur? Well, that had to do with the increased efficiency of the nitrogen. It was either able to stay in solution longer or stay closer to the root system for a longer period of time in order to be able to take that up. And you can see there's quite a bit of a statistic difference between the multiple applications that were done here. We can see, basically based on the leaf nitrogen amount right here, this is actually greater. The leaf N at 28 kilograms of nitrogen per hectare is very close to the similar of the NPK program along with compost. So this is just co-composted biochar and NPK versus compost plus NPK. And then you can see here, if you add biochar plus compost plus NPK, you're getting massive amounts of nitrogen into the plant versus the percent that's available in the soil. You're looking at almost 30% that's making it in. So that's a very, very efficient, a very high rate of nitrogen that's making it in. Of course, now you can see here 140 kilograms of N per hectare. You're talking about a pretty significant amount of nitrogen that's also being applied. Woo! So when we look at this here, we're actually looking at the grams of dry matter. This is going to be, after these plants have been harvested and dried down, the difference in the weight of the biomass of the plant. So this is going to be everything from the top growth to the root system. And what's really interesting to me right here is when we look at 140 kilograms of nitrogen per hectare applied as a control, performed statistically at about the same as 28 kilograms per hectare when applied with co-composted biochar. To me, we're talking about, you're looking at what is that? 4x the nitrogen right there, almost 5x the nitrogen rate, 4x, and you're getting about equal performance there. That's significant. If we look here at the plus compost, right? So co-composted biochar, low rates with additional compost was performing at about the same as compost or just the biochar co-composted and an NPK program at 140 kilograms an acre. So, you can really get a mega ton of performance out of relatively low rates of nitrogen with the addition of biochar that's been co-composted with manure. And if we look at these percentage differences here, 305% versus the control of just NPK, 160% versus the control of just NPK. That's pretty massive. And then if we look here, this talks about how doing 2 extractions over just pure biochar in combination with NPK sprayed over top of it versus biochar that's been co-composted with manure plus an NPK load. Again, you see here you're extracting 6.2 times the amount of NH4. Your ammonium. Your nitrate, you're getting 162x extracted. Your organic nitrogen, 6.2x. Your dissolved organic carbon, 2.1x. Phosphorus, 1.5x. Potassium, 2.6x. So it's a pretty significant amount that's being stored in there that's able to be delivered over a period of time. So we know the backbone of our product is this biochar that's been co-composted with poultry manure and then homogenized with NP and K, right? Because we know as a company, as turf managers, as researchers, that the most important part of any fundamental agronomic program is managing your NP and K levels, right? Those are your macronutrients. Those are what those nutrients are going to be used, have the highest demand of the plant. So if we can start there, anything we add on top of that, right, should be gravy in terms of efficiencies within the plant. So, do we try and trick it out with just sources of NP and K? Because you can do that. And some sources, like for instance, potassium acetate, is going to be faster, more efficient to be taken in by the plant than say like sulfate of potash, right? So do we do it that way, or do we do it this way where we take, something like poultry manure, co-compost it with biochar, and alter the release effects of it after loading it into this carbon carrier, right? So we knew we could develop the NPK portion of it. Then we could develop the soil portion of it. And when I say soil output portion of it, I'm talking about, organic material, applying organic material to the soil, applying compost to the soil. We looked at that. We know the benefits of it. We know the benefits of biochar. There's lots of data out there that shows the positive benefits of biochar. There's lots of data out there that shows negative impacts of biochar. But we knew we corrected that issue with the source of our biochar, the temperature of our pyrolysis process, and the co-composting process. So we've got those two things figured out. Now, we wanted to have a piece that would have a direct physical impact on the root system of the plant. And traditionally, over the last couple of decades, the true workhorse on that has been humic acid and kelp. And so I'll show this study here, which is out of Virginia Tech. This was 15 grams of humic acid applied in combination with 5 grams of seaweed extract during a drought, applied every 2 weeks over, I can't remember the length of time. I want to say it was like a 3-month period. And you can see the root system that was generated in a drought. That's massive. That's good. That is a big, big thing we want. But why peptides? If we're seeing this, why peptides? Well, there's a little bit of unpredictability that goes along with it. So what we know also from Virginia Tech is that under the right environmental conditions, especially if they're mild environmental conditions, biostimulant programs were relatively, it says here, minor effects on Kentucky bluegrass. I'm not going to use that. I'm going to say inconsistent in terms of results. And as they state here, when to consider using your biostimulants during sod or seed establishment, that makes perfect sense to me. That's a great time to develop that root system and that plant mass as quickly as possible, especially in the summer, hot, dry years. So the study they particularly performed on and got the best results from was during drought. Applying it every 2 weeks in a drought at a high rate resisted a lot of the effects by a couple of weeks of the drought. Plus, you had the added benefit of the greater root mass that occurred because of it. Most likely, humic acid or kelp or biostimulants are not going to increase wear tolerance recovery. No big deal. Home lawns, not a whole lot of that going on anyway. Bermuda grass, this has kind of a little disappointing. Justification of use is most likely questionable. No effect on overwintering seen, and perhaps kickstart on spring rerooting. Now, that actually is nice because when you're trying to get your lawns greened up as quickly as possible, humic acid, kelp, other biostimulants seem to have a good effect there. But when we are looking at this, and because some of the improvements that we're seeing were not statistically significant, we have to question as a company whether or not it is cost effective for us to put this into the product. And so here's another one, again, looking at granular humate applied at 2 pounds per thousand. Does it reduce the nitrogen requirements of Bermuda during the summer? We see an increase in CECs. That's positive. Leaf nitrogen content increased from 3 to 3.5%. That's actually positive. A higher leaf end typically correlates with higher turf quality score ratings. But you're only talking about a 0.5% increase there. So not really a big jump. No other nutrient increases, meaning there was no phosphorus levels that increased. There were no potassium levels that increased. No strong visual color differences, but they did not measure the root system. So there could have been some pretty big impacts there. And with CECs, what we looked at is that because we use biochar, and biochar is known specifically for having such high CECs, that when it comes to a granular product for us, that was what we needed for our CECs. We just use biochar. Because with biochar, not only do we have an increase in CECs, which would allow us to draw on things like potassium, calcium, and magnesium, but we also have the anion exchange capacity, which could allow us to take on things like nitrogen and phosphorus that something like a granular humate would not allow us to do. So when it came down to it, for dollar, we felt like we could get the performance out of the biochar and not have to rely on humic acid, therefore save that money and put it towards something where we could get a bigger bang for our buck. And so that's where we began testing. We began researching first, then we began testing, then we began teasing it to see if it would actually be a viable type product. So why peptides? And I think this is most important here when we talk about why peptides, is to talk about what exactly is a peptide. And so in order to understand a peptide, we have to understand what is an organic acid and what is an amino acid. An amino acid is an organic acid. It's a building block of life, right? Amino acids are very strong chelators. They have an amino group that's attached to a carboxyl group. A lot of humic substances are considered carboxylic acids. So very similar structurally. However, amino acids obviously are literally building blocks for living organisms, where typically humic acids are going to be building blocks for decomposed material, not something that's living. Proteins are constructed that are just like really long chains of amino acids are going to be your proteins. Shorter chains of amino acids are going to be peptides. So why peptides? Still can't answer that question yet, because first we have to talk about amino acid products. Not all amino acid products are the same, nor are all peptides the same. So when we're talking about amino acids, what's most important that we look at is how is the amino acid extracted from the protein, and also what is the protein source, right? Lots of things have protein. I'm full of protein. My muscles are full of protein. Protein can come from milk. You think whey protein, casein protein, protein from beef, protein from soft tissues. There's lots of different things that contain proteins. Beans, leguminous materials have proteins. So which one is going to give us the result we're looking for? Because what we're looking for is root action. We've got the CEC action. We've got the NPK action. We've got the soil effect action. We've got the AEC action. Now we need to directly stimulate the root system. What's going to give us that? So we came across a piece of research here, and this is direct from one of the PhD agronomists for Harrells. Actually, Harrells and us actually have the same peptide we use. They have it in a different product. We use it in granular form. And I'll cite their PhD agronomist here. The story begins in 2011 with a group of Japanese researchers. The researchers identified a specific peptide coined the Root Hair Promoting Peptide, or HPP, that increased root hair growth and adventitious root formation when applied to Brassica rapa. The same peptide is found in Harrells, also in Carbon Earth products. This specific peptide is derived from soybean. It does not come from animal proteins. It does not come from soft tissue proteins. It does not come from random crop residues. It is specifically from soybean, and it is extracted using enzymatic hydrolysis. And it's not just any kind of enzymatic hydrolysis that actually derives this material. So this was discovered in Japan, right? And the way they were able to extract this particular peptide was they started with a bacteria called Bacillus circulans. And it was one particular portion of it that they called HA12. They screened it. Well, first they grew it to about 50,000 different strains. And then they screened that down to 21, the most highly protease producing strains. So the ones that had the highest enzymatic action, they had to put it down to 21. Then that was when they started adding it to the soybean meal. And the enzymes that digested the soybean meal fastest, so completely in 48 hours, broke apart those proteins in 48 hours, was actually the single protease enzyme they were looking for that had the highest repeatability in producing this peptide. Get my monkey head off the screen. All right, so when we look at this, and this is kind of the first thing they did. First, they identified the peptide. Then when they took it, they applied it to plants, and they compared the response of the plant to this peptide versus the response of this plant to chemical fertilizers versus a control of just water. And and they name it relative yield here. The relative yield from water to chemical fertilizer was 21% increase. And this would be our fresh weight in grams. Then if we look at from water, our control, to the degraded soy proteins, this would be our peptides that we're talking about that have been through the protease enzymatic extraction, we see 125%, which is a 25% increase over water. Now, that does not mean it outperformed chemical fertilizer, because that's probably statistically not significant in terms of the difference there. But what it does show is that similar to chemical fertilizer, it actually supported many different functions of the plant to get to the point to be able to mimic the type of yield that a chemical fertilizer would give you. And we can see that the soy proteins, the soy peptides, actually have an analysis of a 0.7, 0.1, and roughly 0.3. So not enough of a fertilizer, and it did not contain nitrate. So therefore, it was deduced that the growth promotion of the plant was directly caused by the bioactivity of peptides. So when I talk about these peptides, it's all about the roots, right? So the next part of the study was looking at which phytohormones are going to impact different parts of plant functions, right? So the first thing was ethylene. Take a look at, ethylene specifically influenced root hair and adventitious roots and epinacity of the plant. Auxins affected adventitious roots, cytokinins enlarged leaves, and gibberellins influenced shoot growth. Root hair promoting peptides specifically had the greatest impact on adventitious roots and also root hairs. We can see here on adventitious roots, it got double plus because of the effects it had. You can see the rest of these, gibberellins, it didn't really have effect on anything other than shoot growth. And for root hairs here, we see ethylene was the strongest of all the other phytohormones in the plant. So since we know both ethylene and root hair promoting peptides have the action on root hairs, let's compare the two and see what they do to root hairs. When we look here, ethylene, the phytohormone, which would be here on C, unfortunately causes spiraling of the main root. And this can cause problems because if you've ever seen a root system choke it out, but this is an unnatural growth cycle. So that means something is being forced to grow in one direction that it does not want to grow. But we look here compared to the peptides, figure B, straight root, and that is a significant amount of root hair formation that took place. These bars here indicate 1 millimeter. So you can see you're almost getting 1 millimeter of growth over and over again in terms of root hairs. When it comes to surface area, that is extreme. Again, just to highlight, the main root by ethylene, though it did produce a significant number of root hairs, ultimately it did cause harm to the root system. Initially, the thought was, well, maybe these peptides are actually having a phytohormonal impact on the plant, right? Well, not necessarily. So what they discovered was that ethylene increased the number of root hairs by converting atrichoblast to trichoblast. But it was not replicated the same way in the terms of peptides. Peptides were not converting atrichoblast to trichoblast. Therefore, it was not a phytohormonal response that was taking place in the plant. Rather, it is a signal to the plant that could be even genomic that was telling the plant to produce a greater number of root hairs. And this is going to be with peptides and without peptides. We can see our trichoblast and atrichoblast here, 335% increase, 86% increase, 190% increase, 32% increase, 1,560% increase. That's almost 1,600%. That's almost 16x increase in root hair surface area. That is statistically significant. That is huge. But again, I think it comes back to the question, so the first hole is, what other peptides are there? Because you can put together all kinds of different chains of amino acids and form tons of different peptides. What do the other ones do? So they began testing those and how they affected specifically root hair density. Alkaline protease from HA12. So this is from our bacillus strain. Over 300% relative root hair density. Our closest is subtilicin, which is just over 200%. So 100% difference between the two. It's not really comparable. That is statistically significant. This, in turn, we're building our case. We're building our case. Why are we using these products? So what it comes down to is that first and foremost, we are a research and development and manufacturing company. And in order for us to be successful long-term in this, we have to be innovative. We have to be nimble. We have to stay on top of things. We have to stay involved in the industry. We have to keep our nose to the floor, and we have to be able to pivot in a moment, because everything about this industry is evolving. And if we're not evolving with it, we'll be left behind. And as much fun as we're having, unfortunately, we want to keep doing this for a long period of time. We're all living our dreams right now, right? So what's most important to us is to be innovative. And with that innovation, that allows us to be a good research and development company and a manufacturing company. If we don't have the innovation, we'll never be able to meet the other pillars. So we were seeking out specific actions out of each of our ingredients. We wanted NPK because that is a solid fundamental agronomic program. We wanted to have a positive impact on soil structure, on till. And I love to coin the phrase, the root cycling effect. What's important to me is that we also focus on root development. The higher amount of root hair surface area, the higher amount of root depth, that's going to allow us to find and mine and allow greater nutrient uptake through exudation. Exudation, again, amino acids exuded by the root system to break apart things like our oxides, our ferric oxide, or phosphates that are insoluble. Break those apart, pull them in, and let them be used by the plant. Allow that root system to become the miner of the soil. So while this has been a really long fluff piece here, what's most important that we remember is that at the end of the day, all of this is just fertilizer. It's not that my fertilizer is better than anybody else's. The only thing we tried to do was to make something as complete as possible, cut down on the number of applications for the applicator so you don't have to run to the truck and grab a different backpack. You could just put one thing in your hopper, go spread it, load up your Permagreen with 2 bags of fertilizer. You've got whatever you need in your tank. You go make one pass across the yard, be done with it, right? So I was inspired in this industry by my Permagreen. That was, very first piece of equipment I had that really made this thing just out of control fun for me. And to fit in line with that, I wanted something to make my life easier with my Permagreen. And so part of developing this, part of developing CRRP, part of developing Carbon Earth, part of developing Carbon X was all about how to make the life of the applicator easier. And it's to be able to allow the applicator to get down more with only one single application across the lawn. So it's our goal, it's our ambition, it's who we are as Carbon Earth. It's what makes Carbon Earth, is to develop a product that is as complete as possible, that checks as many boxes as possible. CRRP is our answer to that. You know, when we start talking about the environmental aspect of it and the amount of different instances where we're going to be facing weather extremes, right? So over the last 5 years managing turf, especially where I've been in the transition zone or even further south, it's been really difficult because of the wild weather patterns. CRRP is our answer to have something in there that could potentially affect water holding capacity of the soil, right? Is one application going to make all the difference in the world? No. But if it does gain us an extra week, that's a big win for us. Applying it with a biostimulant that has a direct effect on stress by forcing a root system to be able to mine its way into cooler soil, to be able to mine its way deeper into the soil to potentially find more water. That in turn would fight stress. That in turn would eke us out and buy us a little more time before the effects of environmental conditions begin to set in. CRRP was our answer to that. To get away from plastics and resins and polymers, while they're great, don't get me wrong, there's lots of positive things that come from that. But could we develop a product that worked alternatively without the reliance on that? You know, we look at our waterways and you hear about plastics in the ocean. You know, is there something we could do as a manufacturer? And again, with the idea of being the preservation of our industry, could we develop a product that could be applied and mimic a lot of those results of something that is polymer coated without having to use a plastic? But most importantly, CRRP, Carbon Earth, our product line is our best foot forward to show our environmental responsibility. You've heard me say it before, and I'll say it again to wrap this up. We are stewards of the environment. We're stewards of the planet. It's our responsibility. All right, everybody. I hope you enjoyed this video. I enjoyed putting this together. I hope it makes a little more sense to you why we chose each individual component that we put into every one of our fertilizers. There is a purpose for it. It begins with the agronomic value of NPK and having a solid fundamental program. It moves on to number 2, having a direct impact on soil structure, soil till. And number 3, having an impact on the root system. We are going for total plant nutrition. Not to say we're the only product out there that does it. We're the only one that does it with CRRP technology.
Ain't nothing gonna stop this. Ain't nothing gonna stop this fire.
All right, everybody. I appreciate you watching. Y'all have a good one. Take it easy. Thank you so much.